Hey guys, I know that this is less than ideal. I don't really like it either, but we got to cover some material and I have to be out of the building, so uh, let's make the most of this. So we left off at single replacement reactions. So that's going to be the third new type of reaction that we've seen. Single replacement reactions, the way that you're going to recognize them is that uh, the reactants are always going to be one element, one lone element, and one ionic compound. That one lone element is going to try to replace its counterpart in the compound. And so a metal is going to go into the ionic compound and try and replace the metal that's already in the ionic compound. A nonmetal, if it's the lone element, will try and replace a nonmetal in the ionic compound. But you're never going to match things up. It's never going to be two metals reacting together, and it's never going to be two nonmetals reacting together because, like I said, it's always going to be one lone element and then one ionic compound. So you're going to try and replace the thing that is similar to you. But, all right, so I'll give you a second. You can write this down if you need to. All right, I guess you can pause the video, but I'm going to click on the next slide. What? How did the area change? This is no good. What? There we go. All right. This is only going to happen, so not everything can replace everything, so it will only happen if the lone element is more reactive than the element that it's going to be replacing. Remember earlier when we talked about why reactions happen in the first place? They're to increase stability. Well, you're not going to get a reaction that a less reactive element replaces something that's more reactive than it, creating a less stable compound. That's just not going to happen. So it's always going to be the more react if the lone element is more reactive, then it can possibly replace the one in the compound. How are you going to know what's more reactive? Well, you're going to get this thing called an activity series. And the activity series, you'll have it on your test. You don't have to memorize this. It's on your homework. It's to the right of the page on part 5. And so the way that this works is that think about it like rankings. So the strongest, the most reactive thing is at the top, and the weakest, the least reactive thing is at the bottom. So just like, sports rankings or boxing standings, you would expect something higher up, it can defeat anything beneath it. But if you're in the middle of the pack, right? Well, if you take on calcium, so if you're iron, if you take on calcium, you're going to get your butt kicked. But iron could totally beat copper in a competition. So you can beat anything, you can defeat anything beneath you, but you can't beat anything that's above you. So that's how the activity series works. No. What? All right. Sorry, we're just going to have to live with that. So here's an example reaction. Solid silver is dropped into zinc 2 sulfate. So the first thing you'd want to do is write out an equation. So solid silver, that's Ag, zinc 2 sulfate, so that would be ZnSO4. And you'd need to check your activity series. All right, so let's see. Silver is down here, and zinc is up here. So since silver, the lone element, is beneath zinc, silver's not going to be able to replace zinc. So this reaction isn't going to happen. So you would say no reaction because silver can't displace zinc. All right, let's take a look at another one. All right, so aluminum is added to solid copper 2 carbonate. So aluminum, it's Al. It's a solid because it's aluminum, and we all have had dealings with that, and all metals are solids at room temperature except for mercury. And then solid copper 2 carbonate. So copper 2 carbonate would be CuCO3. All right, and then we got to see, let's check that activity series, and we have aluminum is right here and copper is down here, so aluminum can replace copper in the compound. Aluminum is more reactive than copper. So now we're going to stick aluminum with carbonate and copper will be on its own. Now it's not just going to be AlCO3, not going to happen, because when you build an ionic compound, you always do it according to their charges. So when we write aluminum carbonate, so aluminum takes on a 3 plus charge, carbonate takes on a 2 minus charge, so it's going to look like copper solid plus Al2CO3 3, and then you would need to balance this. Did I balance? I don't think I balanced. So in terms of balancing, you would need to put, let's see, 3 carbonates there, 1 carbonate, so you need to put a 3 in front of that guy. That would mean you'd need 3 lone coppers, and since there's 2 aluminums in the formula unit, you'd need 2 aluminums over there. Oh, wait, I did do, all right, cool. Good job, Vix. So there you go, there's it balanced. Next up, so that's the end of single replacements. They're not too tough. Just remember to combine things according to their charges. The next one is going to be double replacement reactions. For double replacement reactions, you're going to have 2 ionic compounds as the reactants. So, and in those ionic compounds, both of the metal ions are going to switch places. And let's all agree, pairing up the metals with the metals and the nonmetals with the nonmetals would just be silly. All right, they are going to, 2 metal ions would both be positive, they would repel one another. And 2 anions, they're both going to be negative, they would repel each other. These reactions will only happen if one of the potential products is insoluble in water. So what happens, ionic compounds, when they meet up with water, if they are soluble, they will split apart into their individual ions. If they are really, really attracted to one another, then they will stick together. And so you're only going to get reactions when the ions are really, really attracted to each other. Or, in a special case, if a hydrogen ion and a hydroxide ion come together, they will make a water molecule, and that is much, much more stable than the free ions, and so you make a water molecule. So we'll see an example with that. Oh, okay, so this idea of how will you know if it is insoluble? Well, you have solubility rules, and those solubility rules are at the bottom of part 4 on your homework, and they will be on your practice test, they will be on your check, and they will be on the unit test. So you do not have to memorize these solubility rules. So here, so how do we know if something is soluble or insoluble? You follow these rules. So like alkali metals and ammonium are, and hydrogen gets lumped in with them, are always soluble. Acetate ion, always soluble. Nitrate, always soluble. Halides are almost always soluble, except for silver halides. And okay, halides are halogens that have taken on a charge. So you've got fluoride, chloride, bromide, iodide, and then there are just a couple of exceptions for halide ions. There's silver halide, mercury halide, mercury 1 halide, and lead 2 halide. And sulfate ions are almost always soluble, except for some of those alkaline earth metal ones, and then lead 2. Things that are always insoluble, except for if they are already covered in part 1, carbonates, chromates, phosphates, sulfides, oxides, and hydroxides. All right, you do not have to remember, I can't say it enough, you do not have to memorize those solubility rules. So let's take a look at this. If aqueous sodium acetate were poured into aqueous magnesium chloride, so the first step is you have to figure out what are the potential products of this reaction. Well, sodium is already with acetate, so sodium, if they're going to switch dance partners, sodium would have to then pair up with chloride. So the possible product would be sodium chloride and magnesium, the other metal, with acetate. So the possible products would be magnesium acetate and sodium chloride. And then again, why are there 2 acetates with magnesium? Because of charges because magnesium's a 2 plus and acetate is a 1 minus. So here are our possible products. Are they going to be soluble or insoluble? Well, let's see. Acetate ion. So right there it says acetate ion is always soluble. So that means magnesium acetate is going to be soluble in water. And then sodium chloride. That first rule was that alkali metals, including sodium, are always soluble. And so NaCl also soluble. So this is going to be no reaction because neither of the products are soluble in water. Now let's talk about the different ways that we can write out double replacement reactions. So there are 3 ways that we can write out a double replacement reaction. There are the general equations. Those are the way that we typically think about writing out an equation. Ionic compound plus ionic compound yields another ionic compound plus another ionic compound, and then you'd balance it and do all that jazz. Ionic equations. In an ionic equation, anything that is aqueous, anything that was soluble, is going to dissociate into its ions. So everything that is aqueous gets split up into its individual ions. And then in a net ionic equation, you take your ionic equation and anything that's an ion on both sides of the reaction. It's an ion on the reactants, it's an ion on the products, then it gets canceled or reduced away. So anything that is an ion on both sides of the reaction is canceled. All right, so there's probably a lot of writing that you want to do here, so take a minute, pause it, whatever you got to do. All right, so then let's go back to our, we'll look at this reaction again, and we'll write it out all the different ways. All right, so general equation. So you had, oh man, that's so ugly. All right, so you got sodium acetate plus magnesium chloride produces magnesium acetate and sodium chloride. All of them are aqueous. So then when we go down to write the ionic equation, everything that is aqueous, which is everything here, will get split up into its ions. So you get so the 2 sodium ions, 2 acetate ions. So 2 sodiums, 2 acetates, 1 magnesium, 2 chloride ions, and then it yields, so this guy broken up into ions, magnesium ion, acetate ion, and then this guy broken up into ions. 2 sodium ions, 2 chloride ions. And then for our net ionic equation, all right, so there's just this written down here, but then sodium is an ion on both sides, so you could cancel that away. Acetate is an ion on both sides, so that could get canceled away. Magnesium is an ion on both sides, so that could get canceled away. And then chloride on both sides, that would get canceled away. And so this is a no reaction. If you pour these 2 things together, you get nothing new. You just get a mixture, and so no chemical reaction occurs. Aqueous sodium chloride is poured into aqueous silver nitrate. So here's another example that we can look at. So sodium is already with chloride, so it would try and switch dance partners and go with the other anion, which would be nitrate. And then silver, which has a 1 plus charge, is going to try to go with the chloride. So our potential products are sodium nitrate and silver chloride. And then let's check out the solubility rules. So sodium nitrate, well, we have sodium is always soluble. We also have that nitrate ion is always soluble. So poor sodium nitrate never stood a chance. It is definitely soluble. And then we got silver chloride, and then there's this thing here. Halide ions are almost always soluble with one key exception. A silver halide is insoluble. So this guy, silver chloride, is insoluble. All right, so this reaction is going to happen. So let's try writing that one out. So the general equation, so we had sodium chloride plus silver nitrate right? And they were both aqueous, yields sodium nitrate, which is aqueous, and silver chloride or silver 1 chloride, which is a solid because it's insoluble, so it's not going to break apart. So it's just going to stay together as an ionic, which ionics are solids. So then we're going to split that into its ions, that into its ions, that into its ions, but silver chloride will stay together when we bring it down here. So sodium ion, chloride ion, silver ion, nitrate ion, sodium ion, nitrate ion, but this guy stays together as a solid. So then when we go to do the net ionic equation, we're not going to cancel the things that are in silver chloride because they aren't ions on the product side. So you got sodium will cancel out, you got nitrate, which cancels out, and then there is our net ionic equation. Chloride ion, silver ion, those two crazy kids meet up and produce solid silver 1 chloride. All right, and one last example. So we've got aqueous sodium hydroxide is poured into aqueous chloric acid. So you're going to have sodium ion going, okay, so chloric acid is going to be hydrogen with a chlorate ion. So sodium is going to go with the chlorate, and then hydrogen ion is going to go with hydroxide, which is OH minus. And so you're going to end up with sodium chlorate and the hydrogen ion from the acid and the hydroxide ion from sodium hydroxide. And you can write it as HOH so you can see the pieces. It also makes it easier to balance sometimes, but HOH is H2O, it's water. We don't even need the solubility rules because we know from earlier on that having water as one of our products means that the reaction will happen. So don't even need to bother with those. If you have a acid which produces hydrogen ions and you have something with hydroxide, it's always going to react. It's actually an acid-base reaction, which we'll learn about later, but those ions are going to form water, so it's definitely going to happen. So our general equation, we have sodium hydroxide reacts with chloric acid. They were both aqueous to form sodium chlorate, aqueous, and liquid water. So this is going to get split into ions. This is going to get split into ions. This is going to split into ions, but water stays together. So our ionic equation looks like sodium and hydroxide and hydrogen ion and chlorate ion, sodium ion, chlorate ion, water together as a liquid. And then we would copy this down to here, and sodium is an ion on both sides, so gone. Chlorate is an ion on both sides, so cancels. And so we're left with our net ionic equation. Hydroxide ion plus hydrogen ion yields liquid water. So, and that is the end of this presentation. That is the end of Unit 5. And so work on some homework, right? Be cool. My suggestion, do the first 2 from each section on the homework. The substitute should have a copy of the homework answers, but they're also posted online. And so go through the homework, try different pieces, make sure that you can do them, work together, and I look forward to, don't forget, you have a lab. So Friday we're doing a lab, so you need to do the pre-lab. There are extra copies in the front should you need them, but there's also the pre-lab you can do online, or the pre-lab you can do on notebook paper. So, whatever suits your purpose. You could probably do the pre-lab right now on some notebook paper in addition to working on some homework. So I look forward to seeing you guys on Friday, and make the most of the rest of the block.